Well, I'm going to go ahead and we'll just get started with introductions. Hi, I'm Sam Cohen. I work for Levi, Ray & Shout. A little background on myself. I'm a retired IBMer who worked in the VM world since 1983. I'm still working in the VM world. I also work with VSE in its various and sundry forms. Linux, I started working with Linux when it was still the Marist distribution. And I do a lot of, I have a bit of time because I'm working for LRS. I'm doing a lot of pre-sales and post-sales support. We're an IBM distributor. And as a result, I can get a lot of my curiosity out of the way to say, what if, what happened? And because I'm also helping to provide information to folks as part of services, I try to share some of that here at the VM Workshop. And so I'd like to thank the VM Workshop for having me in presenting. This is something I've given before. It's geared toward people that really don't know what the heck, sort of what does VM do? Why does it do it? And what the heck is, people have heard of virtual machines, virtualization, usually VMware. Now, for those of you that aren't aware, VMware is not the originator of virtualization on computers. Within IBM, been doing it since 1964. We kind of have an idea of how it works and how it works better. And the history of it was that it was designed because in those days, computers were big, bulky, expensive, and people were small and cheap, so to speak. And so as a result, the need in the labs was to create the virtualization so people could test out their versions of OS, DOS, and TOS, which were the three operating systems for the mainframes. OS became ZOS, DOS became VSE, and TOS got tossed. So this was, it was developed in the labs. It kind of escaped out into the public in something called CP67. So you can guess when that got out. And from there, it gained a little more formal recognition, knowledge. And so I'm going to go over the concepts and a little bit of what it's about. I may get into a little bit of detail. If your eyes start to glaze, that's okay. If you really want to be fire hosed, come to my session tomorrow on fiber channel protocol and how you set up SANs to work with mainframes. And that's all it'll be basically showing you how the sausage is made when it comes to disk I/O. But we're not going to do that today. So anyway, so today, essentially what we're going to talk about is the concepts of what goes into an operating system design, very high level. VM concepts, their components. Some of the details behind CMS, which is the operating system you run when as a person you want to interact with VM's components. Some of the common commands, a little bit of detail, maybe, depending on our time. And when you're running guest operating systems like Linux under VM, some things to think about. Because you can just basically plop an operating system to run inside a virtualizer. But there might be some things you want to tweak to take advantage of some advantages of what the virtualizer can do for you versus what the virtualizer can take away from you. So if I talk about operating system design, this is not a college class. Basically, there's two fundamental design principles involved when you're going to write an operating system. The operating system's function ultimately is the control of the computer's resources, memory, processor execution, running some kind of a program, and doing things like driving I/O. And I/O is not just disk or tape, it's also to a console device, etc. But ultimately, you make a couple of questions. How many tasks am I going to support at one time? And how am I going to dispatch work? And the two concepts would be priority or interrupt based or time slice. So if I look at that, just some examples of the kinds of things when PC-DOS came out, it basically ran one thing at a time. It was a single tasking environment. And it was pretty much a priority base in that it was only running one thing, so there was nothing else to dispatch at the time. When that one thing finished, then you could do the next thing. Now when you come into the Windows world, and especially your Unix and your ZVM, those are time slice mechanisms. Essentially, what's going to happen is that they are, everybody gets a slice of time. And that's different from ZOS and VSE, which are priority driven, and that you have, the higher the priority, the more time you're going to get. And if you're lowest priority, in the case of VSE, you may not get any dispatch time at all. In the case of ZOS, you can put timers in there anyway. But the primary thing is that your job priority is going to drive who gets dispatched. You're ultimately, let's face it, you're limited by the number of real problem processors you have, but you can have a lot more dispatchable tasks possible. It's making the operating system is making the decision as to what do I send first to those limited number of processors. But when it's a time slice, everybody gets a slice of time. It might be a long time, but it's still going to get something. It won't be totally blocked out. So, as I mentioned, ZVM is a time slice type of environment. And then you make different decisions on your programs when it's time sliced than when it's priority driven. This is why, if you're familiar with CICS, that's the transaction processor for VSE and ZOS, it is designed to run in a priority or interrupt driven environment, not in a time slice one. They tried to introduce CICS for VM and it bombed big time. Similarly, when you try to do something that is more human interactive, like CMS, Conversational Monitoring System, which we'll talk about, they ended up putting a human interaction environment in VSE called ICCF, which runs under CICS, something totally separate called TSO in ZOS. Let's face it, TSO's a dog. From a performance perspective, from an execution perspective, it runs better in a time slice environment than it would a priority, but you're given that thing that the operating system runs in. So, just the way they work. So your best fit is that your application and your business problem should run in a tool that matches up the performance characteristics that you need. That's just some background. So, ZVM does provide for the definition and management of virtual computers. It is a hypervisor. So there's going to be some terminology I use here. The concept of a user is just another name for the name of a virtual machine. Originally, when you could create a virtual machine in which you were running your OS, DOS, TOS, but you could also be having individual humans running it. And in the days before personal computers, you essentially had a personal virtual machine in which you could do things like email, calendaring, all of this stuff. IBM had a product called Profs, which became Office Vision and then basically went away, but there were some wonderful things about it. They were easy, and it was up 24/7 by 365. Let's not talk about Windows. Anyway, the key here in a virtual machine is that a virtual machine only has virtual hardware. There is no real hardware in a virtual machine as far as the virtual machine goes. You can have mapping of real hardware to a virtual machine. You can have virtual hardware, in other words, a construct, a memory construct of hardware in a virtual machine. The operating environment inside the virtual machine doesn't really necessarily know the difference whether or not it's real. There's something out there, like a spinning disk or a bubble of solid state something, or bits on a tape, or just something in memory somewhere, who knows where. So that's why I mentioned virtual hardware. A virtual machine has only virtual hardware, which may or may not map to real hardware. Now, again, I mentioned that this came out of a need for, in the days of old hardware and old computers. What made up hardware in that day? So around 64, 67. So what we had was, this is out of order, but I can't figure out how to resequence this. In front of every piece of real hardware, you had a controller or a control unit. In the case of disk, you had a disk controller. DASD stands for Direct Access something drive. Storage drive device. So your storage devices are down here, and there's a controller up there. The controller was the interface where your channel connections, basically your cables, went from the controller to the server. You didn't go directly to the individual devices. You had the same concept. There's the mainframe. So you had a bunch of peripherals. The mainframe basically consists of the problem processor and memory, and these interface cards with cables. Now, originally the cables were copper cables that were running parallel work. You can think of it as old printer cables or parallel cables. They had a whole bunch of them, and the traffic was going out across all of these, and there'd be 8 or 16 because your bits are a byte, 2 bytes, etc. You could only go so far because impurities in the copper would cause a lag. Your entire sequence wouldn't all reach your destination at the same time. So you had limitations in distance, because if it got too far apart, then the machinery at the other end couldn't put that byte or 2 bytes back together again. Nowadays, it's serial and it's fiber. Okay. Not unlike what we see nowadays again. In the PC world, we went from parallel, now it's all serial, USB, etc. But the key here is that you have the connection going to these controllers. So you have a disk controller. You had combination devices of a card reader, card printer, a card reader, a card punch, and a line printer. Those would have a controller built into the single device. You would have a terminal controller with a console right here. Now, when you bring up a PC, for example, whether you have a graphics interface or a Unix workstation, you have a console device. It's the one that's sending all those startup messages to you. So the concepts haven't changed too much. They've gotten smaller, they've gotten faster. Network, by the way, was also an out-of-bounds, an external device. Something called a front-end processor, from which you had telephone wires, eventually LAN connections. And nowadays they've gone and moved this inboard onto cards on the mainframes. But the concept ultimately is kind of the same thing. It's still a peripheral device. It's just now we're on the bus as opposed to going out over a fiber channel. But the concept of a computer, circa 1967, when this got out the door, are what you find for definitions of a virtual machine defined under ZVM. Now, there's components that make up ZVM. ZVM's made up of a lot of different components. The main one I'm going to talk about is CP, or the control program. This is the guy that manages real resources. creates and manages virtual machines, controls the dispatching of the virtual machines. All of that stuff happens under CP. So there's a lot more detail. One of the cool things, again, because in a virtual machine you have all virtual resources, I can create structures that may or may not exist in the real world. In the logical partition world of the IBM Z, there's a couple of rules that go on. One of which is you cannot have more logical processors or processors assigned to an LPAR than there are physical. So if I have a machine that has, say, 10 processors, I could not give an LPAR 12 logical processors. The most I could give it is 10. I can decide if I want to share what processors I have, all or a subset of the actual physical processors. I can dedicate, I can share between LPARs. In the VM world, I can actually create virtual processors. It is not a good idea from a production standpoint to have more virtual processors than I have logical processors. But if you want to test your limits, you certainly could define if VM has a capacity of 64 processors, you could test your programs against, hey, what happens if I have 64 processors? And you can do that in VM. Will it run well? No, not if you're mapping, say, to 3 logical processors, which means you have at least 3 physical processors, which is trying to be shared with other LPARs. But you have the ability to create these kinds of virtual environments. I have memory over commitment. In the LPAR world, there is no memory over commitment. Part of its securability certification is that an LPAR has memory and nobody else can touch it. But VM is designed, unless you take specific actions, in a shared memory construct. And that's why we have paging, which, if you're familiar with swapping, there's technical differences between them, but the reality is it's a way of handling overcommitment of memory. So I can overcommit a lot as long as I have that back-end disk so it has someplace to put all that virtual memory in. And VM can take care of getting all this stuff set up when it's ready to dispatch. Does that make sense so far? I'm trying to make the difference here between your physical, your logical, and your virtual processors. There really is a difference, and this is one of the ways in which that and memory overcommitment are two of the big ways in which VM is different from LPARs. Notice I'm not saying better or worse. I have my own opinions on that. Now, in the case of that card reader, card punch, line printer, they are now represented as spooled devices. Spool actually is a peripheral. It's an acronym for simultaneous peripheral operations online. Wasn't that a handful? But the word spool, which people use pretty well throughout the industry, is an acronym that came from this environment of we're going to represent these real devices as virtual devices in the case of JES2, in the case of VSE Power, in the case of ZVM, spooled devices. So as far as the virtual machine is concerned, they all will have at least one card reader, one card punch, one line printer. They will also have one console. And the cool thing about a virtual console is it doesn't have to be connected to a physical terminal. If you want to use it and type at a keyboard, yes, it does. But your virtual machine always has online to it the virtual console. So if you're running an operating system that is sensitive to having a console connected, if it doesn't like, if it does bad things if a console is disconnected, and there are some operating systems that do that, when you're running under ZVM, you don't have that issue because the console is always there, but it's a virtual console. When you log on to the guest, I'll talk about that in a few minutes, then you are connecting your terminal as a physical console to the virtual console. And you are there until you disconnect your physical terminal from the virtual console. So that's the point of this. So a lot of this is dealing with terminology. But these are the terminologies, and this is why this stuff exists.
So even though it's disconnected, it still works.
It still works. You still, as far as it's concerned, the operating system in there is concerned. It has a console that's up and running, and it's sending stuff to it, and it's presenting it.
Okay.
Nobody's there to see it.
Who's replying to this?
Well, if you need to reply, it's going to sit there waiting. Just like as if you were sitting there and you're out to lunch, physically, not mentally. Now, for disk devices, one of the things you can do in this realm is suballocate. And so you could think of it, if you're used to what you can do in the PC-DOS world, where you can suballocate a disk into logical partitions, as you might do in the Windows or DOS world, or you could do in the Linux world, where you can break it in. And in fact, in the Linux world, you may have at max, depending on your type, 3 primary partitions, and then you have the concept of extended partitions, things like that. We have that, but we don't have that primary and secondary partition stuff. We can go in the case of count key data, and count key data. Well, I'll talk about that in a moment. But essentially, we have two different types of disk architectures: fixed block, which is what you usually see on quote open systems disk. Those are half kbyte blocks, or variable blocked. And you'll see them referred to as count key data or extended count key data because of the nature of how that stuff works. But ultimately, that's variable blocked disk versus fixed block disk. A mini disk is a suballocation at a cylinder boundary. In the case of fixed block, it could be as small as, in theory, 1 half kbyte block, but you're not going to do much with that, because it won't even have room to put in any kind of a directory or table of contents or anything else at the front of it. But your granularity is basically from 1 to the size of that physical device, however it's been allocated, whether it's X number of terabytes of fixed block or X number of, it's at a cylinder boundary in VM for the variable blocks. Make sense so far? Now, one of the things, though, a mini disk cannot physically span a disk. It's limited to the size of the individual disk unit, or LUN. You could not span a LUN with a mini disk. It has to be contained within that physical device. Now, what else do we have that we can have for physical and virtual devices? I have them listed up here. We can have virtual hypersockets. We can have virtual switches. We can have virtual coupling links. If you're going to run a parallel sysplex inside of a ZVM LPAR, you cannot span, in the VM cluster world, you could not have a coupling facility link going from one LPAR to another LPAR. It has to be in the same LPAR. But we also have some virtual peripherals for stuff you really don't see much anymore. Channel-to-channel connections. Don't worry about what that is. You don't see it much except when you're setting up a cluster. and that's a link, that's a high-speed link that could be unidirectional, could be bidirectional, depending on either the physical connection or what you're connecting. But it's a way of connecting two different LPARs without using a protocol stack like IP. So that's just some of the stuff, physical as well as virtual. So now if we really want to get into the computer 101, if you're a ZOS guy, a virtual machine basically is an address space. From a Linux perspective, you could think of it as a process. But there's a higher degree of isolation because CP ensures that whatever is going on in one virtual machine, unless you have opened up some communication to other virtual machines, they are absolutely isolated from each other. It's unlike a Linux or a ZOS where things are happening that involves the operating system heavily. And the reason for that is because when CP sets up, when it's dispatch time, CP sets up a virtual machine to be executed and then basically issues a command, start interpretive execution, or a SI. What that does is that says, hey, virtual machine, you're on native hardware. And it gets out of the way until it's asked to do some service or its time slice expires. That's quite unique compared to other virtualizers. It's completely out of the way. You don't get into the virt.io. If you have a dedicated communication line to a virtual machine and that virtual machine is driving it, it really is driving it. VM CP stays out of the way unless you've asked it to do something on behalf of the virtual machine. So as a result, it is very high performance and with a high degree of symbiotic relationship between what the operating system can do, what CP can do, and what the hardware can do. Now, that's VM as a concept. Let's get into the details of what happens when I boot up an LPAR that's running ZVM. I'm going to boot up from a disk or a tape, or maybe via FTP, but not for much longer. To start something up, what we're doing is we're going to load something into memory, and then it's from memory. It's the problem processors will be told go boot from an addressable device. And what happens is that it boots up. Has everybody here seen a load screen for an LPAR? Has anybody not seen? Okay. What happens is that when you start up a logical partition at the hardware, there's two parameters. One is what is the I/O address? It's a 4 or 5 character number, hex number, that represents a disk or a tape or some device. Where am I going to go to pull my information from? And then there's something else called a load parameter, and that is 8 characters, up to 8 characters, that is uniquely interpreted by whatever's booting up at that address that you told it from. If you're booting off of a SCSI device, a WWPN and LUN are provided as well. So you would say, I'm not only going to go out to this address of this SCSI network port, but here's the WWPN and LUN that I want to talk to on the other side. Otherwise, there's this thing called an I/O subsystem that has the mapping of what is the equivalent of a WWPN and LUN inside of it, and that unique address maps to a unique WWPN and LUN inside the I/O subsystem. In the case of SanDisk's fiber channel protocol, that stuff is different. That's my spiel tomorrow. So it goes out, reads the stuff in. CP begins to get loaded into, it's loaded into and starts executing on your problem processor. Now, a problem processor could be a general purpose engine. It could be an what's called an IFL. It's a specialty engine for Linux. And those are the two types that ZVM can boot on. And what it will look for is it has some parameters in there that will say, go look for a file at a certain place on the disk that I told you about and get something called a system configuration file. And what that system configuration file is going to say is, what do I need to bring up? What do I need more information on? What should I start? What should I bring online in terms of peripheral devices, of which those have been told with? CP will talk to the I/O subsystem and say, what do you have for me? And it goes out and says, hey, who are you? And it's building its control structures at boot up time. But it also, you're going to tell it, okay, what am I going to call you? And do I have any virtualized hardware that I want to define early on in the process? If I'm going to be part of a cluster, what's my cluster information? How do I talk to the other cluster members? And we don't want it to be too much of a cluster, so you want it to be well documented and easy. If I wanted to create what we call command classes, I'll talk about that later, and there's other features. There are billable features of VM, such as, well, it used to be TCP/IP, it's not now, now that's included, but the directory maintenance feature, or RACF, the IBM security server. If you have those are additional charge features that need to be enabled. And there's an enablement flag that goes on inside that system config. So there's all this info that say, how do you get stuff started? Another part of that startup is loading of something called the VM directory. Now, the VM directory is what defines every virtual machine that CP could create and dispatch on. Now, there's a couple of things I have here as kind of warnings. The key here is that the virtual machine definitions, and I'll show you an example in a moment. It basically says, what's the name of the virtual machine? What resources does it have? And then, what can it do? Part of that mini disk definition that I had from before, the definition of a mini disk, in other words, what disks, what suballocation of a physical disk do I have, and what is its I/O address, and where is it? There is no sanity checking if somebody else in the VM directory is using that same space or a part of that space. Doesn't look for overlaps. So you have to be really careful that you don't have one virtual machine overlapping an area used by another virtual machine, or they're going to step on each other. And if you want that to happen, that's fine. If you don't want it to happen, there's going to be some real strange things going on that'll be hard to explain, where it looks like somebody from outer space came in and zapped part of your disk because you didn't know. The other piece is that this source file that creates the directory is compiled with something called DirectXA, and there's no disassembler. So don't lose your source. Now, this is an example of an entry in the VM directory with three types of entries. First of all, a profile that you see on the left side is, you could think of it as an include deck. When you have common definitions, then having an include deck avoids you having to put the same thing in 6, 8, 10, 100 times. The nice thing is that if you need to make a change to everybody, you make it here and it will just flow down to anybody that includes it the next time they log in. Now you see in this are information that would be common to a virtual machine definition. In this profile, what happens is that it says, okay, I'm going to start out with my virtual machine will be 2 gig large, and on the fly, it can grow to 8 gig. I'm going to have CP command classes B and G, and don't worry about what those mean. Here are a couple of commands I'm going to define here within my directory. I don't have to run a CP command from a CMS system before actually booting up my environment. Here are my spool devices. Here's my console. This Linux main, that's a secondary user ID. In other words, any message going to this console will be sent to the virtual machine named Linux main if Linux main is logged on. A NICDEF is a virtual NIC. Here are links to disks. These 3 are for CMS, the CMS operating system. This is an example of perhaps some startups that might be common if I was doing a shared disk environment. And you see these Linux common. Here's an example of the Linux common are definitions that would have a read-only access. That's what that R means, multi-user read. So lots of folks could see it. So if I was starting up CMS to do some setups and say, hey, if you're Linux 1, do this. If you're Linux 2, do that. Then I can do it there and then boot up from a different operating system. Here then, in my Linux 1 guest itself, I have some unique names, unique guests. Maybe this is my / or my root file system. This might be something else or vice versa. But this is the kind of thing where when I want to create a new Linux, these are the only definitions I have to worry about. The rest of them will just flow out from my includes or from my common. Any questions? Have I lost anybody yet?
Restate the obvious. So you basically define a paragraph there on the left, profile, and then you're inserting that exact text into the user statements over here by saying...
They'll be read at when you log on. CP will see that it's included and pull it in from that.
That makes sense?
Yeah. You can think of it as a .h and C. Now, inside a virtual machine, I'm running an operating system. I can run entire operating systems that could run outside of VM, such as ZVM itself, ZOS, VSE, TPF's another of the big operating systems, are very specialized. Linux, of course. Key here is it has to be an S390X architecture build because it's not going to recognize some of the control structures or the language of x86 or any of the others. But then there are here a couple of operating systems that exist solely within the VM world, one of which is the Conversational Monitoring System, or CMS. The other is Group Control System, or GCS. The key here is that just because you're running an operating system under ZVM, if you are trying to run, let's say, a ZOS version or a VSE version that cannot run on this hardware, it still can't run under this hardware, even under ZVM, because VM, as I mentioned, is going to do the start interpretive execution, turn basically the operating system over to run on the real hardware, and if it can't run on that native hardware, it'll blow up. It'll probably blow up right at its boot most of the time. You'll see that because these are, in today's world, these are all native 64-bit environments. And so if you have a 31-bit, it has to be, announced or certified to say, I can tolerate being in a 64-bit. So just be aware of that. It's just because you can run a virtual machine second level, it could be a full ZOS or a VSE, still has to be able to run on that level of hardware. Now here are the components, and there's a lot of components. I mentioned CP, CMS, GCS, don't worry about GCS. Dump viewing, Rex. Rex is built in, it's the procedure language of VM. It's also the procedure language for VSE, ZOS, Regina, you can usually get for some other platforms. Rex is incredibly powerful. It's primarily a parsing language. Some folks, you know, if they're used to Python, they'll see some similarities. The one thing I'll mention about Rex is that its relationship with CMS pipelines gives it an amazing amount of power to do things very, very efficiently. I can write a complete TCP/IP socket call, send, retrieve, and that includes the open and close all in one pipe stage, and I could do that within a Rex routine. So I could do some parsing in one way, send stuff off, get it all back in one stage, manage it within, and it's amazing what you can do, very flexible. Servicing tool, that of SMP and ZOS, and be it, DNF, or whatever you're using in apt, in the case of Linux, MSHP and VSE, here it's VM-Sys. The rest of it, don't worry about it. Language environment is still there, so if you have programs you're running in COBOL, PL1, and C, they have a common library, common language environment to run those programs, just like you could run the same language environment and basically library calls on the other main operating systems. Then there's some of these other components, TCP/IP built in, HCD and HCM are ways of managing the I/O configuration. It's required on ZOS. It is not required in VM. Whether you use it or not is subject to discussion. You have DFSMS. It is not pre-installed. It's orderable. It's no charge. You need that if you're going to have a virtual tape system, like a TS 7700, 7800, whatever the current one is. You need that piece to do the management. These others are in there. I mentioned RACF, Domain Performance Toolkit. Other things you can get, optional program products. Tape Manager, Backup and Restore, Ops Manager is being talked about today, the cloud infrastructure, Z-Secure, lots of stuff. I'm going to touch on this because we're going to run out of time here. So CMS is the interactive operating system for VM. It is now multitasking. And in a lot of cases, it's used to set up an environment. Rather than doing commands at the directory level, which are only CP commands, you can do change. You might set up your virtual machine environment and then bump it up to boot up then from your Linux. A lot of people don't know CMS has a full screen mode available to it. It's not just a line mode. File systems here, the mini disk file system, I call it. It is record-oriented, access control, be careful, get my spiel on directories from this morning to talk about that. There's also shared file, which you could think of as like, if you know Logical Volume Manager, this is a spannable, but it's record-oriented. Byte file is similar to shared file, uses the shared file structures, but that's a byte-oriented environment as opposed to record-oriented. CMS has 26 mount points, A to Z, 26. They're mounted, and files are referenced by a name, a type, and a file mode, not unlike what you see in VSE or Windows or Unix, should you choose to. Keys here is there's no path statement in this environment. Searches, when you ask to run a program, it's going to search A down to Z. And then there's some well-known or common file types. Something with an exec means that it's in the procedure language. Some others. Key here, and these are common mount points when you start up CMS. A is your work disk. It's either your root shared file directory or your 191. If you have a second work disk, it's mounted at file mode D, the operating system at S and Y, and tapes tend to be in the 180 area. Just command processes, just touching on this if you're going to write in Rex. And these are some common CP commands: log on, log off, or log out, IPL. There's query and set, depending on what you see, depends on whether you're talking to CP or you're talking to CMS. To know that, you look in the lower right corner of your screen. If it says VM read, the virtual machine is waiting for a response. If it says CP read, CP is waiting for a response. That's how you would know who you're talking to. By the way, VM, great help. When in doubt, type help. Help at a task level, help at a message level, help at a command level. Lots of help. So these are just some common commands. I expect that you'd want to pull down. This will all be posted tonight at the VM workshop. So feel free, this is already mine, the head's already full at this time after lunch. The hardest part about being a VM sysprog is knowing which side of the looking glass you're on. Am I looking at the real world or the virtual world? And that's the challenge. And then some thinking. Memory overcommitment, just some comments from my experience. For the most part, in a Linux world of running Linux virtual machines, usually at a 1.5 to 1, like a 50% overcommit of memory is usually pretty safe. But if you're running databases, they might not. If you're running all databases, you might need to be closer to 1 to 1, as opposed to 1.5 to 1. Be sure that you tune your environment. Throwing hardware at it, more virtual memory, more virtual processors, may actually cause it to run worse. What you may find is tuning your workloads to be the smallest that you need will give it better results, because now your operating system in that guest doesn't have to work as hard. You find the balance. A little bit of paging is not a bad thing, or swapping is not a bad thing. It says that you're using and not over wasting memory. Leave it for somebody else. But you have to plan for growth. So you have to find that balance depending on what you're doing. Don't follow your rules of thumb for other hardware or virtualization platforms. They don't count, because this thing is different, because it does things smarter. And lots of stuff, online, offline. The Linux VM has some kind of cool things in it, even though it hasn't been updated in a long time. Okay, I'm pretty much out of time, but any questions, or you can just come see me afterwards. I hope this was helpful. I know it's a fire hose. So, they'll set up, there's bound to be couches out there somewhere for everybody to go, ugh. But thank you so much for attending today. I hope you found this helpful. And again, if you need to, my email's on the front. Give me a holler, and we can talk and help you any way I can. Thanks so much.